Hello friends, in today's question on heating water, bubbles being formed at the bottom of the vessel detach and rise. Take the bubbles to be spheres of radius r, making a circular contact of radius small r with the bottom of the vessel. If small r is very much less than capital R and the surface tension of the water is given as T, the value of R just before bubbles detach is given by. So in this there is a slight mistake in the option. There is no factor of 2, so let us add a factor of 2 in each of the options. Okay. So this will be here multiply by 2, and here also let us suppose multiply by 2, and here also 2, and here also 2. Okay. So every option is multiplied by 2. So in this case we are given that we have a bubble of sphere of radius r, and there is a small at the bottom, and it is given it is having a radius of small r, it is having capital R radius, and angle is given as theta. So there will be two forces acting on it. One will be the bind force in the upward direction, and the other force will be the force of tension T, which will be acting in the tangential form, and one component of this surface tension T will be acting vertically downward. So we are going to start from there only, that there are two forces acting on this sphere. Okay, so we say forces acting on the bubble. And first force is our bind force. Bind force acting on the bubble acting on the bubble is equal to the weight of the liquid displaced. Weight of the liquid displaced. So we can write the bind force if represented as Fb, and this Fb will be equal to 4 by 3 pi r cube density of the water, and we have G. So this is the bind force acting in the upward direction, and the second force will be the surface tension. Surface tension acting along the circular contact, acting along the circular contact of radius small r, and in the vertical downward direction as a vertical component, in downward direction. So we can write that our surface tension force Ft will be equal to 2 pi r multiplied by T, and we have this as sine of theta. And if theta is very small, you can say for small theta, sine of theta can be approximately equal to small r upon capital R. Therefore, we can write that our Ft, substitute the value, we get this as 2 pi r, and this is our T, small r upon capital R, and we can just adjust the things here. So we get our Ft will be equal to 2 pi T divided by capital R, and this becomes small r square. So we got the surface tension force, and this will be acting downward. And the buoyant force will be acting upward. So for detachment, condition for detachment, upward force is equal to downward force. So we can say condition for detachment, condition for detachment, upward force is equal to downward force. So which basically means that our Fp is equal to Ft. We substitute the values, and we get Fp was our 4 by 3 pi r cube we get this as 4 by 3 pi r cube rho w multiplied by g is equal to 2 pi T divided by capital R, and this comes as small r. Pi goes with pi, this 2 cancel with 2. So we get that our small r, that is r square, will be equal to 2 by 3, and this becomes r4 density of the water multiplied by g. So now it is quite simple. We can write that our r will be equal to, this comes r square, square root of, sorry, I forgot to mention t here, so this comes t. T, and this becomes 2 by 3, and r square, we have this as rho omega g upon t. So this is the radius of the, which were asked for, the radius of the bubble just before detachment. This is the radius of bubble just before detachment. And the option that are given to us, option number A will be the correct option. You can write that option A is correct. Option A is